Good morning. So, today we will continue our discussion with respect to the Schrodinger's equation. So, the Schrodinger's equation mathematically has 3 terms. The first term on the left hand side is nothing but the Laplacian term in space, is the spatial derivative, and this particular equation describes the wave function, and this wave function can be anything. It could be for an electromagnetic wave or a pressure wave, and you have the second term, which is the potential energy constraint, and the term on the right hand side is the temporal derivative, describing the evolution of this wave function in time. So, the operator that is shown here, represented here, is called the energy operator or the Hamiltonian operator. So, we will see that the will show that in the today's class, that expected value or the probable value of this Hamiltonian is the energy possessed by the electron or whichever electromagnetic wave. So, the Schrodinger's wave equation originally conceived by Schrodinger, and however, he did not physically understand the relevance of this wave function. So, it was Born who gave a physical interpretation to the wave function. He says that the wave function itself by itself does not carry much meaning, but if you take the product of the basically psi star, which is the conjugate of this wave function, and multiply it with the wave function, this will give the probability of locating a particle somewhere. So, therefore, according to the normalization condition, so to find the particle somewhere in the infinite space from minus infinity to plus infinity, so the product of this psi star psi should be equal to 1. And not only that, so in order to find out the expected or the probable values of other quantities, such as the actual coordinate. For example, the actual coordinate is represented by r, it could be x, y and z, x comma y comma z. So, this is obtained by again minus infinity, integrating minus infinity to infinity psi star into r psi. So, if you are talking about this is your physical space, so this is dx. So, if you same thing should be with respect to the integral psi star psi dx should be equal to 1. So, the same thing can be extended to other derived quantities. We will look at the most important ones today. For example, you can also have a very common representation, some capital omega, which is some quantity that you need to know the expected value. So, this is always obtained as minus infinity to infinity psi star omega psi dx. So, where omega could be the coordinate r vector, it could be the time, it could also be the momentum, and it could also be energy. So, you need from the Schrodinger's equation, finally what you are interested is all these quantities. It could be where the particle is exactly located within the infinite domain, and what is the exact time of location of this particle, what is the momentum possessed by this particle, and what is the energy. So, you see in quantum mechanics nothing is 100% sure. So, there is always an uncertainty given by the Heisenberg's uncertainty principle. So, we only call this as expected value or probable value. So, we know that in the real world that also we are governed by several probability, but always we go through them and we know for sure that the probability has become a possibility. For example, when you take a train or a bus, there is only a probability that you will reach a place B. So, anything can happen between place A and place B. So, according to quantum mechanics, so this is only a probability that you will reach a certain place B, could be 80 or 90%, okay. But finally, you reach that place and you know for sure that it has become a possible 100%. So, therefore, in quantum mechanics, although we know that these things really are there, I mean there is always some uncertainty associated in estimating these quantities, okay. So, these are therefore called as expected quantities, and especially these expected quantities become more probabilistic at very small scales, because the values themselves are very small, right. So, the values of energy or momentum, they themselves are so small that you cannot estimate them with great accuracy of the way that you are estimating the macro scale variables. For example, if you take temperature at room, okay, and you have 2 or 3 different thermocouples. So, each thermocouple will be having a 0.1 or 0.2 degrees error by itself. So, one thermocouple will read, for example, 25.5, the other will be 25.6, but still both are supposed to be fairly agreeing with each other, because their individual uncertainties are plus or minus 0.1 degree Celsius. Okay. Now, in the small scales, the actual value that you are measuring is less than the uncertainty itself. Okay. When you are talking about resolution, if you are resolving something less than 0.1 degrees, then there is a lot of uncertainty in that measurement, okay. And that is why the entire quantum mechanics deals with these kind of uncertainties. Now, what is the momentum operator that we have to use? Okay. If your capital omega is your momentum operator, now these momentum operators are very specific. So, you have to exactly know how they look. So, this is given by this particular derivative here, okay. That is nothing but in the Cartesian coordinate system, this is d by dx. Let me use unit vector as x, because I already used a complex variable I and I do not want to confuse that. D by dy, this is the unit normal, d by dz. So, this is basically the momentum operator, okay. So, we just put this momentum operator into this, that means you take the derivative of the wave function, right. You take the derivative of the wave function and you calculate this, and then you multiply it with the complex conjugate and then you integrate it, and that should give you the expected value of the momentum. You understand? So, this is the operator, but in order to calculate the expected value of momentum, so this operator has to be substituted into this particular expression here to get the expected value. We will see that, we will do some examples slowly. Similarly, you have to understand the energy operator. The energy operator is represented by this Hamiltonian symbol H, okay. And how do you calculate the energy if you look at particle picture? It is basically the momentum square by 2m plus your potential energy u, right. So, this is your kinetic energy, this is your potential energy. Now, if you look at p square by 2m, you can also write this from the momentum operator here. You can substitute for p into this particular expression, right. So, what does that give you? So, therefore, the Hamiltonian H will be, so you have minus I H delta the whole square. So, what do you have? Minus I into minus I, minus 1, okay. Minus of modified Planck's constant square into, so this becomes Laplacian divided by 2m the whole square. No. So, minus I into minus I. So, I square is minus 1 and then you have another minus. So, it is minus. I square is minus 1, minus of minus plus, again you have another minus. You have to be careful. It is not minus I into I, it is minus I into minus I. Okay. So, you have therefore, minus h modified Planck's constant square del square by 2 m, okay, plus you have u. Okay. So, you remember now if you go back to the Schrodinger's equation, the structure of the Schrodinger's equation on the left hand side. So, if you just multiply this by the wave function, so this is basically the operator that is on the left hand side of the wave equation. So, that is why we call that operator as the Hamiltonian or the energy operator, because the energy operator itself is nothing but minus h square del square by 2 m plus u. So, on the Schrodinger's equation now will be therefore h psi will be equal to minus I h bar d psi by dt, correct. So, okay, so this h is nothing but this Hamiltonian h, right. And now we will see what is this Hamiltonian and how is it actually related to the energy. So, if you now take the expected value of this Hamiltonian operator, okay. So, now this is just the operator. Now, we need the expected value of this energy or the Hamiltonian. It turns out to be the actual energy. We will see this now in a short while, okay. But you just understand that this is what you get. And now, the one more caution with respect to the use of this particular order, we have psi star omega psi dx to calculate the expected value of any quantity. We should be careful that we cannot simply switch between psi and psi star, okay, especially when you have these gradients and Laplacian operators. So, they will be different if you operate your psi with del and then you multiply it with psi star, that will be different from operating on psi and multiplying with psi star, okay. So, if for example, you cannot flip this and say this is psi omega psi star dx, especially if your operator omega will involve gradient or del square. So, that is with the momentum and energy operators. For position operator it does not matter, you can flip between psi and psi star, but you have to be very careful that this order is always what you have to follow, okay. So, the order of taking the derivative and then multiplying is very important, okay. So, the other thing that is also of interest in quantum mechanics is the uncertainties. Right now, we have found out the probability or the expected value, but what is the uncertainty in the determination of each of these quantities, because in quantum mechanics uncertainties are very high, okay. So, therefore, we need to also use a expression. So, the operator for uncertainty. So, again in uncertainty also you have what is called as expected value of uncertainty, okay. So, the uncertainty itself cannot be certainly stated. So, there is an expectation of uncertainty there, okay. So, for example, if you look at definition of standard deviation. So, in the real world the standard deviation is the indicator of uncertainty, right. So, how do we define it? For example, standard deviation in some quantity x, how do we define? We take 1 over square root. If you have say n points, you have n minus 1, okay, I is equal to 1 to n. We take the difference between the actual value minus the mean value. So, the mean value is your, I use this operator here to state that this is the mean value and square of this. So, this gives you the uncertainty in the real world. Similarly, in quantum mechanics there is an analogy, but we cannot exactly translate this to that. In quantum mechanics we calculate the uncertainty in some quantity, let us say q. So, the expected value of the uncertainty now turns out to be square root of again integral psi star and then q minus the expected value of q, because the particular quantity minus the expected value of that, okay. And we take square of this, multiply it again with psi dx, because you see this any quantity, if you want to calculate the expected value, you have to always multiply psi star with that and psi dx, integrate it. So, that will be a common theme. Okay. Now, if you want to calculate expected value of uncertainty, now this uncertainty itself is the value minus the expected value the whole square, okay, and then the square root of that. So, this is the quantum mechanical way to determine the uncertainty of, it could be in energy, it could be in momentum, it could be in position, it could be in time, q could be anything. Okay. So, the expected value of uncertainty is always estimated using this particular equation here. Okay. So, from this we can actually show, we will do some examples today, tomorrow and the next week. We can actually prove that the Heisenberg's uncertainty principle is always satisfied if you calculate your uncertainty from this particular expression. So, that means Heisenberg's uncertainty principle states that if you consider, for example, the location of a particle in space. So, you cannot say for sure it is exactly located at a particular position. So, there is a uncertainty associated with its location, or if you say that that is located exactly here, that means there is a problem with the momentum. Okay. So, therefore, in general it says that the expected value of uncertainty in momentum multiplied with the expected value of uncertainty in position should always be greater than or equal to modified Planck's constant by 2. So, this is one of the uncertainty theorems. The other is with respect to energy and time. So, instead of momentum and space, you can also transform this into a space of energy. So, expected value of uncertainty in energy and time. So, should also satisfy your uncertainty condition, which is like this, right. So, you have to basically know these things as facts, so you do not have to worry about how they came, whether they will be satisfied. They will be satisfied if you work out simple problem and you will be able to calculate the uncertainties, multiply them, and you will find out that this will always be satisfied. Okay. So, now what we will do next is to go ahead and try to solve this Schrodinger's equation. So, now I have stated, I have given you the Schrodinger's equation, also how do we calculate the expected values of many derived quantities such as momentum, energy and so on. So, then we have to now go ahead and solve for the wave function. Only if you know the wave function can we substitute and calculate all these expected values. So, therefore, how do we solve the Schrodinger's wave equation? So, what we will do, so now if you see the nature of this, this is a wave equation, and not only that, it is a partial differential equation, and if you look at the entire equation like this. So, you have a spatial derivative on the left hand side, you have a temporal derivative on the right hand side, and we can start with a simpler case, maybe where we can ignore the potential energy constraint, but if you retain the potential energy constraint, then the solution becomes a little bit complex, especially because you should know what is the value of this potential energy constraint, and usually it could be constant in certain cases, but more often it turns out to be a function of some other variable like x. Okay. So, in that case, then again the partial differential equation will have non constant coefficients, which becomes again difficult to find a direct solution, but still what we will do is we will approach the solution by separation of variables. Okay. So, this is the normal direct method of solving simple partial differential equations. So, how many of you have actually taken course where separation of variables has been covered? Do you? So, only 2 or 3, and how about the rest? You do not know how to basically solve. So, in this particular course I cannot spend one lecture on teaching you how to, but I will just give you procedure and it is going to be similar for other equations. So, with respect to the Schrodinger's equation, now that you have a wave function now which is a function of two variables, one is the position, the other is time. So, we will assume that we can actually find a solution which is a product solution of two independent solutions. So, one which is a function of only the position, the other which is a function of only time. Okay. So, please remember that this quantity on the left hand side is a function of both r and t. So, we are assuming that the partial differential equation is linear, okay, and the boundary conditions are also supporting the linearity such that we can use this assumption where we can say that they are product of independent solutions, one only a function of r, the other only a function of t. Okay. So, not all the partial differential equations satisfy, there are nonlinear PDEs which cannot be solved like this. The other important condition for separation of variables is you should have at least two homogeneous boundary conditions in a particular direction. So, two homogeneous means if you have a two dimensional system like this, in one direction, either in this direction or this direction, you should have homogeneous boundary conditions. So, if you have one homogeneous boundary condition here and one on this side and the other two non homogeneous, again this is not possible, because we need to create an ordinary differential equation called the eigenfunction problem, and this eigenfunction problem can have eigenvalues only in the direction where we have homogeneous boundary conditions. Okay. So, therefore, these are some of the conditions, and fortunately the Schrodinger's equation for most of the basic cases we can find solutions using separation of variables. So, assuming this, and if you substitute into the actual Schrodinger's equation, can you convert the partial differential equation into an ordinary differential equation? So, using this assumption here, so what we are now trying to do is we are trying to transform psi which is a function of r t as psi which is a function of only r, and we have we will use another variable y here, capital Y, which is a function of t. Okay. So, that means we are trying to break this PDE into ordinary differential equations, one in space, one in time, and then we individually solve it. That is the only way of solving a PDE, right. So, can you attempt that? I will give you some 5 minutes time, all of you. So, when you differentiate with respect to space, the term y will be constant and vice versa. Okay. Yeah. For simple cases that we will be dealing now, to understand the basic energy states of free electrons and so on, it is perfectly okay. But again, when we go to some See, most of the basic cases, textbook cases are all solvable using separation of variables. We will see all those cases, particle in a box, we have hydrogen atom, we have rotational systems, all these can be still solved, but only the problem comes when your potential energy constraint is becoming not a constant but a function of some x. Okay. So, still separation of variables will work, but finally the ODE that is left out is having non constant coefficients, and that cannot be simply solved. So, that has to be numerically solved. Okay. So, that will be a problem. So, you substitute this into the PDE and you also divide throughout by psi of r y of t. So, what do you get on the left hand side? So, let me write the equation down and you please verify it. 1 by psi minus h bar square by 2 m del square psi plus u psi. This is what the ODE that you get on one side. Okay. The other ODE with respect to time will be I h bar 1 by y dy by dt. Is that okay? So, this is your converted such that this is now a ODE with respect to space and this is an ODE with respect to time. Now, where is the ODE now? Still this is a single equation. So, you have to see that to satisfy this particular equation we have derivatives, ordinary differential equation with respect to space on the left hand side, with respect to time on the right hand side. So, therefore, these two terms can be equal only when they are equal to some constant, okay, and let this constant be termed as E. Now, I am giving this name E here not by coincidence, because we will show that the expected value of the Hamiltonian is also nothing but this E, and this turns out to be the, what is the expected value of Hamiltonian, that is the energy. Okay, and that is why I am giving this E here. I could give this lambda and then later show that this is nothing but the expected value of Hamiltonian, and then therefore that is the energy. So, in order to avoid all that, I am directly saying that this is nothing but E, which is the energy. Okay. So, therefore, now we have split this into two ODEs. The first ODE will be basically this is equal to E, the second ODE will be this is equal to E, right. So, therefore, if you solve the ODE with respect to time, so that is you now you separated the partial differential equation into two ODEs. The first ODE with respect to time is this, and the second ODE with respect to space is this. So, therefore, you have two ODEs, PD is separated into two ODEs. So, what is the solution to the ODE 1? So, that is a simple first order ODE. So, the solution should be y of t should be some constant C1, let us say. Now, this will be what, exponential function, right. So, you can say dy by y is equal to E dt, and if you integrate it, you have ln of y is equal to E t plus some constant. Therefore, y will be C exponential of what. So, this entire term will go inside. So, you have therefore minus, if you take I on the other side, it becomes minus I, okay, minus I, and you have E, we have by h bar times t. So, this is your solution to the ODE in time. Okay, let us call this as 3. Okay. So, just we will keep this as it is. Now, because the final solution is a product of the two independent solutions, so this will directly be multiplied to the solution for 2. Okay. So, we will just leave it. Now, this is the simplest solution. So, what it says is the wave function is now varying or decaying with time in this particular manner exponentially. So, now what we had earlier discussed about showing that the expected value of Hamiltonian is nothing but energy E can be now proven from using this equation 2. Okay. So, this is what we will show. So, I will just start this and I want you people to continue. So, what is the expected value of H? How do we calculate it? Minus infinity to infinity psi star H. So, now let us write this operator. So, what is your operator H? So, this we will expand. Okay. Okay. So, what we will do is let us not touch the H, we will only expand for psi and psi star. So, psi star is a function of r and t. So, we will use the separation of variables method, we will separate it into the product solution of, so we have psi of r and y of t and this the whole star, this is the complex conjugate of that solution times we have h into we have psi of r y of t, okay, dx. Is this fine? So, we have just used the separation of variables for the complex conjugate and for the wave function. Okay. So, now we use the ODE 2. So, this H of psi of r. Okay, this Hamiltonian is what? The Hamiltonian will be operated only because it is a function of space. So, therefore, H will operate only on psi of r. Okay, so, therefore, this can be written as H into H psi of r. So, this can be actually one more step we can write it psi of r y of t whole star H into psi of r into y of t dx. Okay, so, this is the actual operation that is done. The Hamiltonian will be operating on the psi, which is a function of only position. So, therefore, now we go back to 2 and what do we see from 2? So, this entire term here is 1 by psi H of psi is equal to E. So, therefore, H psi can be replaced by E psi. So, this entire term is now E psi and since E is a constant, okay, so we can actually take this term E out and therefore, this will be E of minus infinity to infinity. So, we once again convert back to our regular wave function psi, which is a function of r and t, psi star psi dx, right. So, this is psi star which is a function of r and t, this is psi which is a function of r and t, E is a constant pulled out. So, what is this? 1. So, therefore, this becomes equal to E. So, we have shown that therefore, the expected value of Hamiltonian is nothing but this E, so which is also the energy. Okay. So, therefore, we can rewrite the equation 2, the ODE 2 in space can be rewritten as minus h square by 2 m del square psi. We can bring the E to the left hand side and we can write this as u minus E psi is equal to 0. So, this becomes the second ODE to be solved. We will call this as equation number 4. So, I am just rewriting this equation here by bringing E psi to the left hand side. Okay. So, now depending on, so to solve this what do we need? We need to know the potential energy constraint u. So, once we know that, this ODE also can be solved for psi and also we need to know boundary conditions. So, how many boundary conditions do we need? Since it is a second order ODE, we need 2 boundary conditions to be specified. Okay. So, now we will go into the solution part. So, the first that we will be, first case, simple case that we will be taking is free particle in one dimensional space. That means you just have some particle like this just in space, okay, and you want to solve the wave nature of this particular particle. So, in this case, what is the potential energy constraint? 0, because the particle is free. So, it is free to go anywhere in one dimensional space, there is no constraint on the particle. Okay. So, therefore, potential energy constraint is 0. This is the simplest case that we can solve the Schrodinger's equation. So, therefore, we already know the time solution. exponential function of time. Now, the ODE becomes much simpler. We have del square psi equal to 0, because sorry. So, we have this is equal to, I am sorry, use E psi. So, u is equal to 0. So, this will be equal to E psi. So, since this is one dimensional space, we can expand the Laplacian here. So, this is minus h square by 2 m, we have d square psi by dx square minus E psi is equal to 0. So, this is a second order linear ordinary differential equation with constant coefficients. You see, this coefficient is a constant, this is also a constant, and this is homogeneous, because the right hand side term we have equal to 0. So, second order linear homogeneous ODE with constant coefficients. So, what is the kind of solution for this? So, we can either write this in terms of exponential functions or trigonometric functions. Okay. So, what we like to do is use the exponential functions here. So, therefore, we can write the solution for psi of x as a e power minus I k x plus b e power I k x, or we can also write this purely in terms of a cos k x plus b sin k x, right. So, either in terms of trigonometric functions or exponential functions. So, this is the solution for this particular ODE. What is k here? So, where k is related to square root of 2 m e and h bar comes outside the square root. Okay. So, we absorbed all these constants into another constant k directly. Okay. So, now therefore, you can relate your energy directly to this constant k here, and what is the final solution? Psi of x comma t. So, we multiply the time solution to this space solution, and therefore, what do you get? A e power minus I. With respect to time, what do you have? Minus I e by h bar t. So, that we will, so we will take minus I out. So, e by h bar t plus k x. Similarly, we have b e minus I e by h bar t minus k x. So, this is your final solution. So, in this case we do not have any boundary conditions, because the particle is not within any system, it is just free in space moving from minus infinity to plus infinity. So, this is your final solution. So, what do you have here? So, you remember our representation of a wave. So, we have used e power minus I omega t plus k x. Okay. So, this we generally use if you have waves running on one direction, and then we have omega t minus k x to represent the waves running on the opposite direction. So, therefore, what this tells you is that you have waves which can run either on the right hand side or the left hand side, and they have combination of waves running on right and left, which are present as the solution to the wave function. Okay. and there is also an equal probability that you have both the waves running on the right and left, because this is a free particle in space. So, you cannot say that there are more waves running on the left than on the right. So, you have equal probability to find waves running on both the right and the left. So, therefore, the first term here will be corresponding to what? Left running wave. Okay, this is your left running wave, and the second term here corresponds to your right running wave. So, final solution is a superposition of left running waves and right running waves, a linear superposition. Okay, so, that is all it is. So, what we are now seeing is the wave nature of one particle which is free in space. So, what the Schrodinger's equation tells you is, in quantum mechanical picture, this particular particle is nothing but consisting of waves which are running either on the right side towards the positive x direction or towards the left side towards the negative x direction, and therefore, the solution is superposition of just these waves, that is it. Okay. And how do we relate this wave number to energy is given by this particular relation here. Okay. So, this is a very simple picture of a free particle. So, to start with, so also you can observe one thing with respect to the Heisenberg's uncertainty principle. So, in this case the position cannot be exactly determined, because it is a free particle, it could be anywhere from minus infinity to infinity, and whereas what about the momentum? The momentum of the particle can be exactly determined here, because you have the wave vector k which is related to constant E. So, all these are constants. Okay. So, therefore, your momentum p is equal to h bar k is now exactly determined from this particular expression. Okay. But still the Heisenberg's uncertainty principle has to be satisfied, because now you have the uncertainty is infinite in determining the position. Okay. So, finally, your delta x uncertainty and delta p uncertainty multiplied together should be greater than or equal to h bar by 2. So, this should be satisfied, although now it says that this is approaching 0, but this is approaching infinity. Okay. And therefore, this product of this will be satisfying the Heisenberg's uncertainty principle. So, for a freestanding wave, so you cannot exactly say the position, it is anywhere from minus infinity to infinity. So, uncertainty is infinity, approaching infinity, whereas the momentum is approaching a very certain value. You understand? So, next we will stop here today. The next case that we will take is the particle in a 1D confinement. So, when we started the introduction to waves, I just solved the simple wave equation for a particle subjected to a confinement, a thin film or whatever it is, and then we got the solution in terms of sines and cosines. We found out the solution for the energy and so on, and now we are going to do the same example in a more rigorous way by solving the Schrodinger's equation. Okay. So, this we will take up tomorrow. So, we will first complete the one dimensional case, then we go to a 2D confinement. Okay. So far in the freestanding particle there is no quantization, they are just continuous waves. Okay. Now, we will see that once you put a confinement, the quantization will start appearing, we will start getting discrete energy levels and so on. So, the real quantum mechanics will start with the confinement.